Section 3.6 is a topic called optimization. You have done optimization before. You haven't had all the tools that you have now, but you've done optimization before in algebra where you look for things like creating something where it has the maximum amount of area inside of an enclosure. We're going to do one with that one. Creating something that has the smallest space or distance around it, things like that. So you're trying to either maximize or minimize something, and you now have things that allow you to maximize and minimize, and they're called derivatives. Yes, they're called derivatives. So we're going to use some derivatives for optimization. That's going to be what's different now that you didn't have when you did optimization in the past. All right, so to start with, some guidelines, and this isn't like steps 1 through 5 on the last thing. I mean, you don't have to do all of these steps. These are to give you an idea of how to think through the problem, okay? So you may use some of them, you may not use some of them, it's all good. Visuals are great. Making a sketch, making a table, writing down some details, it's a good deal. Identifying what you know and what you need to find. That may be sort of in your mind, you're thinking it, or you may actually write it down on paper. Writing down equations, that's something you're probably going to write down. You're going to write down an equation. Within your equation, you need to identify what in the world you're trying to optimize. Are you trying to optimize x? Are you trying to optimize area, and you called it a? Are you trying to optimize perimeter, and you're calling it p? What value is it that you're trying to find the best case scenario, the optimal value for? And you need that to be written in terms of only one variable. Like, for instance, one of the ways that we talk about area, let me just pause here to give you some kind of perspective on this, is we say area is length times width, right? Well, you can't have a variable for length and a variable for width and talk about optimizing area, because then you have two variables on the right. So somehow you got to get rid of one of those variables. That's what it's referring to. The fourth thing then says to determine the maximum and minimum allowable values, if any, for the variables you're using. It's good to be aware that if you're talking about a sheet of paper, we're going to do one with a cardboard sheet of paper, that if the length of the paper is 6, that you can't have an x value bigger than 6, because that would be bigger than the piece of paper you have. Make sense? There's sort of some constraints when you put real world stuff into this that makes sense. You can't just look at the entire graph now and say, oh look, but over here if x is equal to 10, I've got a maximum value. Well, but you don't have any more paper because the paper's not that big. Or something like that. So there's optimal information from the context of the problem. And the fifth thing says to use calculus to find the extrema. So extrema, again, just means maximum and minimum values that you're working with. Okay? So we're going to do one. It's a very basic one that you have seen before, or seen something like it before back in algebra. We've got a 3-sided fence that we're going to build next to a section of river. When I pulled this straight out of your book, but usually when I see this question asked, it talks about being next to the side of a barn, which makes a little bit more sense, because then it's really enclosed, but whatever. Maybe I should have just changed it so it made more sense, but I was just using what your book had. All right, so we've got a fence to be built along the side of a river, and the 3 sides of the fence that we have, plus the side of the river, are going to form a rectangle. And all of a sudden, I have a picture in my head of what this looks like, and you do too, don't you? So let's draw it, okay? So we've got a river. There's our river. And thank you. And then we're going to have a rectangle next to it. Something like that. There are some pieces of information about rectangles that you know. So tell me something.
90-degree angles.
Okay, they're 90-degree angles. What else? They do have 4 sides. And one of my sides is my river in this case, right? The sides are not all equal, but a couple of them are. 2 of them are equal, and that's helpful information for looking at this particular problem. Whatever this value is on top, I'll just call it x. I have the same value down here on bottom. Agreed? Yeah. And I don't necessarily, like Taylor said, have to have the 3rd value on the side to be the same thing. It could be different. It could be the same, in which case this would be called a square, which is just a specific type of rectangle, believe it or not. It is a rectangle as well. But it wouldn't have to be the same. It could be, but it wouldn't have to be. Okay, so far so good. This is my picture. It tells us some information. It tells us the area here has to be equal to 1,800 feet squared. So this area is 1,800 square feet. And we're asked to find the minimum perimeter and then the corresponding dimensions of the rectangle. So how do you find perimeter? Add sides together. So in the picture that I've got here, what would that be?
2x plus 2y.
2x plus
Plus y.
y. Yeah, we want the perimeter of the fencing actually, not really so much the whole rectangle, because we're not going to fence the side by the river. Now, here's the problem right here that I was mentioning on the previous slide. This equation has two variables on the right. You will always be given enough information to eliminate one of those variables. What piece of information have I not used? The 1,800. Very good. That 1,800 gives me some information. It's information about area. What's the area in terms of an equation of this shape? It's x times y, right? Length times width. And I know that it's supposed to equal 1,800. So can I solve for one of these, the x or the y, in terms of the other one? I always can. And that's how the problems will always boil down to. There will be something that you can solve to get rid of that other variable. And it doesn't really matter which one you want to use. Do you want to solve for x or do you want to solve for y? X. Okay. So if we solve for x, x will then equal what? 1,800 over y. So up here in my original problem then, I can rewrite this as 2 times 1,800 over y plus y. So this will become what?
3,600 over y plus y.
Excellent. Once I've gotten the equation into y, or one variable anyway on the right-hand side, I can actually work with the calculus I know. So let's think for a moment here what we've got here. We are told to minimize, find the minimum perimeter, and we have an equation for perimeter, right? The equation for perimeter is in terms of one variable on the right, right? That's the steps over here that we talked about in part 3. Write an applicable equation. In fact, we wrote 2 equations. Identify the quantity that's to be optimized. That was the perimeter. And write the equation in terms of one variable, which we did. So now we're supposed to, well, it would be a good idea sort of to take a look at number 4, just in case we get anything weird. I don't think we will on this one, but taking a look at the maximum and minimum allowable values here, oops, wrong direction. If I'm taking a look at these side lengths and so forth, none of these side lengths can be more than what? Actually, we can restrict it further. 900 is the most I could have for a side length. Because at the very least, even if this ends up being a really tiny, skinny little rectangle, the most that the x values could be is half of the total length, right? The perimeter. The absolute most that the x value could be is 900. What's the absolute most that the y value could be? It would actually be 1,800, because it could be tall and skinny this way, right? So that all of this was 1,800 and the x was this tiny little fraction of I mean, you wouldn't be able to put anything in there. I don't know why you'd do that. You wouldn't. But that would be the idea. So sort of some restrictions here to think about is that x has to be, well, let me write it this way. We don't usually write it this way, but we will. The x value has to be between 0 and 900, and the y value has to be between 0 and 1,800. Now, in this particular problem, if you didn't do that step, you're going to be okay, because the calculations that we're going to do aren't going to actually rely upon this piece of information. But there are other problems you do where you're not going to be okay if you're not being aware of it, and since you don't know at the outset which ones of those problems will have that feature or not, it's a good idea to take a look at it each time. Okay? All right, so what we're going to do then is we're going to take that rectangle, or that blue equation, that P equals 3,600 over y plus y, and we're going to do what with it? Derivative. We're supposed to find the optimal value. That is, we're supposed to minimize this. We want to minimize the perimeter. Right? We want to buy as little fencing as possible, because the fence costs money. I mean, just practically speaking, little as fence as possible. So we're going to take that equation, and I'm going to write it with that y value in the top because it'll be easier to take the derivative of. So this is my perimeter equation, and I need to find the derivative of perimeter. Now, this y is not like the y when we did implicit differentiation. It's just y. Okay, just plain old variable. You've decided to use y instead of x. We're going to treat it just like plain old variable y. All right, so what is the derivative of 3600y to the negative 1?
Negative 3600y to negative 2.
Good. And then what?
Plus 1.
Plus 1. And what do we need to do?
Set it equal to 0.
Set it equal to 0. So I'm going to start with negative 3600 over y squared plus 1 equals 0. What are we going to do next? Solve for y. How are we going to do that? Okay, so I can do negative 3600 over y squared equals negative 1. Can I multiply by y squared? Sure can. So this is negative 3600 equals negative y squared. Uh-huh. So 3600 equals y squared. What does y equal here? Yeah, technically plus or minus 600, but it would have to be the positive because we're talking about a length of fence, right? So we really don't have this going on. It's just 600. We do need to make sure that that really gives me a minimum value. All right? Like, we found that it should be a max or a min, but we're supposed to find that it's a minimum. We need to verify that it really is a minimum. There's two ways to do that. What are they? Number line and test points on either side. What's the other option? Second derivative, and then we'd actually plug in 600. So do you want to take a second derivative, or do you want to do number line? Number line? Okay. We will do a number line. So we're doing a number line. We need to test points on either side of 600. So 1 would be great. We can test the number 1. And then what else?
Isn't it supposed to be 60?
Oh, it is 60. We wrote it down wrong. Thank you. Thank you, Summer. Yes, 60.
1 and
Okay.
100.
1 and 100. Okay, we'll do 100. 1 and 100. Is that okay?
Or 0.
Yeah, we could do 0. That'd be fine, too. Actually, we couldn't do 0 on this one because we have a denominator of 0, yeah. We actually couldn't do it on that one. All right, so we're going to plug it in. I'm going to say let's plug it into, oops. Well, we'll put it here. Plug it into here. So if we plug in the number 1, what happens? You get a negative. If you plug in the number 100, what happens? You get a positive. Negative means the graph is decreasing. Positive means the graph is increasing. So this is a minimum. You have to verify for me that you found something you say you found. Either a number line or a second derivative. You're going to show that step. Okay? That really verifies this really is a minimum. Now, we have to actually answer the question that was asked. The question says, find the minimum perimeter. And it also says, find the corresponding dimensions of the enclosure. You can actually use equations to do that, or you can go back to the picture to do that. Either are fine. I'm going to go back to the picture. If this is 600, 60, oh, still using that 600, aren't I? If this is 60, we could actually talk about then the area, x is equal to 1800 over 60, right? Which would be what? 30. So this is 30, and this is 30, using what we know about the area. So we can talk about the perimeter. What is the perimeter?
X equals 90.
Bigger.
6, 12.
Oh, just kidding, yeah.
How do we find perimeter, guys?
Out of the sides.
Out of the sides, and we have 3 sides,
60.
120. You have a 30 and a 60 and a 30. Your perimeter is 120. 120 what? Feet. And then your dimensions. What are the dimensions? 30 by 60. So we say 30 feet by 60 feet. Or you could say 60 feet by 30 feet. It wouldn't make any difference. What do you think? It's just an application of this idea of doing minimums and maximums for first derivatives, right? Okay.